system with a quadratic potential energy. Okay, so the Hamiltonian total energy over the system is given by E squared over 2m, the energy, and then you have also a 1 over 2 a x squared. Okay, so that's the Hamiltonian, and we'll be looking at solutions to this system of the form H un is equal to En un. All right. Now, if you again remember that the P object there, an operator, is H bar I del x. Okay. So it's a second order differential equation. Now we could solve the differential equation, but there is a nice way of going through this with a factorization method, which is called the operator method. We'll do that first, and then we'll look at the differential equation later. Okay, so one thing that I can do is I can try to put this into some unitless form. Now, to put that into some unitless form, I'm going to divide this by some energy. And one energy I can identify is if I look at the classical frequency, okay, classical oscillation frequency. Okay, that's omega classical. That's just going to be equal to square root of k over m, right? And that means if I take h bar omega c, that has some units of energy. Okay. So if I just divide this h by h bar omega c, now I'm just dividing this by a constant. So I'm just going to get a unitless set of terms here. So what do I get? I get p squared over 2m divided by h bar omega c, which is just going to be equal to h bar times square root of k over m. So there will be an h bar, and 1 over omega c, so it's going to be square root of m over k. The other term will be 1 over 2 k again over h bar, and then I'm going to get again reciprocal of omega c, which is m over k times x squared. So if I just algebra, p squared over 2 h bar square root of m k plus 1 over 2, okay, 1 over h bar square root of numerator, square root of k m over h bar. Let me check my algebra. Right? So I have this now as a dimensionless quantity. Okay? So that means that since P has units of momentum, X has units of distance, this really should be something like P squared over some P0 squared, right? So P0 is some constant momentum given by these terms, plus X squared over X0 squared. Okay? So that both of these things are units. Okay? And we can actually find out what these things are really easily. So P0 squared. Okay, so P0 squared is 2 h bar square root of mk, and x0 squared is equal to 2 h bar 1 over square root of km. Okay, so these are two length scales and momentum scales associated with the harmonic oscillator. Okay, so we'll see how these things come in. At this point, we are just doing some simple algebra manipulating things so that, okay, we are working with unitless quantities, so we have not done any physics yet. Okay, and one thing you can see that if I multiply P0 squared with x0 squared, the square root of km's cancel, and I end up with 4h bar squared, so x0 times P0 is just 2h bar. So I have that relationship between x0 and P0. All right, so that's my unitless Hamiltonian divided by h bar omega c. Now I want to see if I can factor this out, okay, into two terms. And one way I can factor it out is if I just assume that they were simple variables. Okay, remember that P is an operator, okay? So I have to be careful. But if I write this as x over x0 minus I P over P0 multiplied by x over x0 plus I P over P0, what does that give me? Okay, so it gives me x squared over x0 squared. That's nice, that's what I want. Then I get plus p squared over p0 squared. And then there will be cross terms.
I times commutator of x and p.
Okay, let's just go slowly. Okay, so I have the term which multiplies x times p, which comes with an I. So the cross terms will have an I over x0 p0, right? There will be an xp term, and there will be a minus px term. Okay, so ordinarily if p was not an operator, I would say the second term is equal to 0. But since this is an operator and is meant to operate on something, I have to be more careful. Okay, so let's just look at that. If I have xp minus px, okay, operating on any function f of x, what do I get? Okay, so I get x times h bar over I, okay, ordinary derivative because I just have functions of x. Okay, so that's the first term, minus h bar over I dx, again the p operator, x times f now. Okay, and now I have x h bar over I df dx, then I have minus h bar over I, okay, derivative of xf with respect to x, so there will be two terms. There will be an f, and there will also be an plus x times df dx, right? Okay, now you see this last term cancels the first term, but there's a remaining term. Okay, so the remaining term is equal to, okay, if I just put the I to the numerator and change the sign, I h bar times f. So this says if I operate with xp minus px, okay, on any function f, what I'm going to get is going to be I h bar times f. Okay? So that means I can just replace this. I can just say xp minus px is equal to I h bar. Okay, so that is called the commutator of x and p, and this is a useful quantity. We'll write it as x first, p next. Okay, so this is the commutator of x and p. So x and p do not commute. That's our terminology. Okay, xp is not equal to px. There's a difference between them equal to I h bar. Okay, commutators are very important. We'll see how they come up when we look at this more formally. But in any case, now this we have found to be equal to I h bar. Okay, and this x0 p0 we said was equal to 2h bar. Okay, so what do I get when I multiply them together? What? Minus 1 over 2, right? The h bars cancel. There's a 2 here. I squared gives you minus 1. So this whole thing is minus a half. It has to be unitless, right? Because this is a unitless sort of thing. Okay, so you see, I have some sort of factorization, although there is some residue. Okay, so this was my Hamiltonian. So this whole thing was, okay, oops, not that one. This one was h over h bar omega c. And these things I am going to give names, okay, because I don't want to keep writing them. So this thing I am going to call a plus. So the one with the minus sign is called a plus. This one I'm going to call a minus. Okay, so these are now operators. They contain x and p in them. So they contain x and a derivative of x. Right, so what does that give me? H is equal to, okay, everything will be multiplied by h bar omega c. So everything is proportional to h bar omega c. So although we just started this out as a mechanism to get unitless, okay, Hamiltonian, it turned out that everything is proportional to it. And that is going to be equal to, okay, a plus a minus plus a half to cancel that minus a half. Okay, so if I just take this term, add plus half to it, I get my h back. Okay. All right. So what do I do with this? Let's play this commutator game a little bit more. Okay. So get used to doing this because you'll be working with commutators a lot. Okay, so let me ask, for example, the question, what is a minus commutator with a plus? Well, okay, let me just write it down. So I'm going to get x over x0, a minus, so it comes with the plus sign, plus I p over p0, commutator with x over x0 minus I p over p0. Okay, so I have one term commutator with the other, yes.
So I believe for the calculation of h, we should write minus 1 over 2.
No, you see h is on this side, so I am going to move this 1/2 to the other side.
So it is minus.
Minus a half, so it will turn out into a plus plus, right? No, trust me. Okay, you will get a minus sign if this is a minus a plus, for example. Okay, good that you are checking me against the book, but this time I'm right. Okay, so I have this object, okay, for which I want to find the commutator. So how do I evaluate these commutators? Let's just look at certain rules. Most of them are quite obvious, but let's start with a simple one. If I have A with A, for example, what do I get? What's the commutator of A with A? 0, right? Because this is just equal to A times A and minus the reverse order, but it's the same, so it's 0. Okay, what happens if I have an A and a B, but suppose one of them is multiplied by a constant. Let's say this is being multiplied by some constant C. Okay, so I'm going to get A, B, C minus B, C, A. But this is just C is a constant, so this is C times AB minus BA. So I get C times AB. So if I have constants, they just move out. Okay? So the constants just come out of the commutator. I have sums here, so let's look at that also. So it's something like distributivity. Commutator of A with B plus C is what? Well, it's going to be A, B plus C minus B plus C, A. So I have AB minus BA, AC minus CA. So this is just A commutator with B plus A commutator with C. So you have this nice distributive property. Okay, so I can just split the commutator into pieces and just look at these things term by term. Okay, so I'm going to get here terms which will have commutator of x with x, right? Commutator of p with p. Okay, so those things will give me 0, right? So x over x0 with x over x0 is going to give me 0. Commutator of p with itself is again going to be 0. So the only things that are going to give you any finite terms are going to be things like xp and px. Okay? So those things are going to have an I in them and an x0, p0. So this, you see this x0, p0 comes up again and again. Okay? So I, x0, p0, what do I have? Okay, so x commutator with p with a minus sign. Let me use a different type of bracket here. X commutator with p. Okay, it's this one. And then I have plus I p commutator with x. So these things come with opposite signs, but we should really put one more expression on this table here. If I have AB, this is just AB minus BA by definition. So you can factor out the minus sign, so it will be BA minus AB, which means this is minus BA, okay, which makes sense. AB minus BA versus BA minus AB. Okay, so that means this is just the negative of that. And we already have a commutator for x and p. X and P commutator, this piece here was I H bar. This then is going to be minus I H bar. This denominator here is 2H bar, so please do the algebra for me. What do I get at the end? Yes. This just one, right? The H bars cancel, the 2's cancel because there are 2 of them, and I'm going to get a minus I, so it's 1. Okay, so it's just equal to 1. Okay, so this is an important result. We should, at some point, I should start to form a table someplace for these things, but okay, for the time being, let me just write it over here. So A minus commutator with A plus is equal to 1. Okay, what happens if I try to find the commutator of A plus with A minus? Minus 1, right? Our theorem says minus 1. Okay, so these are in the opposite order. So sometimes you can just write these things in one go. Okay, so you can say this is A, okay, with another A commutator is going to give me 1. So you write the upper signs, which are going to be minus, plus, plus. Then you write the lower signs, plus, minus, minus. Okay, so you either read the upper signs or the lower signs. But this is, okay, sometimes confusing, so if you like, you can just use them separately if you like. Any questions up to here? So you have been just playing games with these operators. Okay? Okay, now it's time for physics. We generated all this formalism, and we are going to now try to use it. Okay, so let me just put down my Hamiltonian. H is equal to H bar omega C, then A plus A minus plus a half. Okay, and I have this commutator A minus A plus is 1. All right, so what happens? Okay, so how do I proceed? I'll try to find energy states. Okay, so I'm after H un is equal to En un type of solutions. Now suppose that I have found a solution. Okay, suppose I have a certain solution. I don't know which one of these they are. Okay, but suppose I find a solution, okay, such that I have this H times this U is equal to E times U. Okay, so it's one of these solutions. So the question is, what is H times A plus times U? Okay, so I'm just going to operate on this function. So this is U is a function of X. So very simple. I just multiply this by X. Remember what A plus is, right? I just multiply it by X over X0 and also differentiate with respect to X and add them up. Okay, so that gives me a new function. Okay, so let's just try to analyze this. So I'm going to get here, this H is H bar omega c, okay, a plus a minus plus a half times a plus times u. Okay? So this thing is equal to that. So this is equal to h bar omega c. I have a plus, a minus, a plus, plus 1/2 a plus u. Right? Now, what I'm going to do is I'm going to change the places of these two. Why do I want to do that? Because if I do that, then I'm going to get an a plus a minus operating on u, and for that I know the solution. Okay? I know that a plus a minus is going to give me EU. Okay, so this is, so if I just expand this, this just says that h bar omega c, a plus a minus plus a half u is equal to EU. Okay, so this is given. So I have this a plus a minus on u giving me something simpler. So that's why I want to hit this function u with an a plus a minus instead of a minus a plus. So now how do I replace this a minus a plus with an a plus a minus?
With that commutation relation.
Okay, with a commutation relation. So the trick is if you have something like a minus a plus, what you do is you write it in the opposite order, a plus a minus, and then add to it the commutator a minus a plus, okay, in the same order, a minus a plus, okay, because this is now going to just cancel this term. Okay, so this a minus a plus from our list over here was plus 1, right? So this thing is just plus 1. So that means I can write this as h bar omega c, a plus, then I have an a minus, a plus, a minus, plus 1, okay, plus 1/2 a plus u. All right. So now I have an a plus on the left multiplying everything, so I can factor that out. Okay, h bar omega c, a plus. Okay, then I have an a plus, a minus, right, plus 1 plus, let me write the 1/2 first, 1/2 plus 1 operating on u. Okay, so all I did was I just factored out this a plus. Okay, but now this piece here, together with the h bar omega c, I know what it is, right? So that piece, h bar omega c, a plus a minus plus a half, is going to give me the energy of the system, E, right? So I'll get a plus is still here, multiplying everything. H bar omega c, a plus plus 1/2 u is, according to that equation, E u. But then I also have this 1, which gives me plus h bar omega c u. Okay, or just factoring these constants away, I end up with E plus h bar omega c u. So what happened?
Not also
Yes, I have an A plus. Thank you. Very important. A plus U. Okay. So let's just look at the first line and the last line. So this just says that this is equal to H A plus U. Okay, that's what we expanded and that's what we got. All right. So what is A plus U represent? Okay, it's a solution with an energy, okay, with an energy which is h bar omega c higher. Okay, so I started out with a certain U, and then I operated on it with A plus, so that gave me a different function. So this is my A plus U. Now this has energy E, this has energy E plus h bar omega c. Okay, so I found another solution with an energy h bar omega c higher. But now I can do this again and again. Okay, so I can go up one more step. Okay, I can multiply the original U by A plus twice. Then I'm going to get E plus 2 h bar omega c. So I don't know what E is, but if I can find at least one E, okay, for which this equation is satisfied, then I can generate a whole bunch of E's like that. Okay, now what would happen, what would your guess be if I did this with A minus instead of A plus?
Energy is lowered by minus.
Okay, so exercise for you. When you go home, just try to do this on your own, except that use an A minus in place of U. So I'll just write down the result here. Okay, so H times A minus U is going to be E minus h bar omega c times A minus U. So A minus U is going to give me a function here, okay, which is going to be, okay, so this is going to be A minus U, and its energy is going to be minus h bar omega c. All right, so I get a ladder-like set of states which are all solutions to the Hamiltonian, and energy levels all change by h bar omega c. So you see, for the harmonic oscillator, the energy levels seem to be equally separated. For the particle in a box, remember we had this n squared factor. So if we had n equal to 1, gave us some energy, n equal to 2 gave us twice that energy, n equal to 3 gave us 9 times that energy. Well, whereas here, it appears that these energies are linearly spaced. Okay? All right. But we still don't know what E is. Now, we can find E by looking at the solutions, what conditions these solutions must satisfy. You see, this is a harmonic oscillator potential. It's a quadratic potential. So the potential energy is just 1 over 2 kx squared. So this is what our V of x looks like. Okay, so this is our V of x as a function of x. Now we are finding these energy levels which must all be greater than the potential energy. Okay, so we have these various energy levels. I have found one of them. Suppose this is the value E, Okay, so there's going to be another one, E plus h bar omega c, which I can obtain by applying this operator A plus. And here is another one which I can obtain. Okay, this is E minus h bar omega c. So this I obtain by applying A minus. So I can go up as much as I like to higher and higher energies, but there must be a certain lowest one. Okay, there must be certain lowest energy state under which I shouldn't be able to go. Okay, so if I call this energy some E0, okay, that's going to be the ground state energy. Okay, that will correspond to some U0. Okay, so that's the ground state wave function, U0 of x. Now, when I apply A minus to that, okay, I should get 0. Okay, so the solution should disappear. So I'm going to get, so that implies that A minus times U0 of x is going to be equal to 0. Let's see what energy that corresponds to, because I know that this is going to have some energy E0. So let's see what h U0 is. Okay, so this is going to be h bar omega c, that's my Hamiltonian, A plus A minus, okay, plus a half times U0. But I just said that A minus operating on U0 gives me 0. So the first term is not there. So I'm going to get h bar omega c over 2 U0. Okay, so that tells me that the energy of that lowest state, when I just hit these states repeatedly by A minus, I am going to get to the lowest energy state eventually. But if I hit it one more time, I get 0. And in order to satisfy that, the lowest object must have energy h bar omega c over 2. Now that determines all of the energy levels. So this is now going to be h bar omega c over 2. The next one is going to be 3 over 2 h bar omega c, and so on. Okay, so I have these energy levels, En, which is going to be equal to n plus a half h bar omega c. So in the ground state, we have a certain energy. So this h bar c omega c over 2 is also called the 0 point energy, which means that a harmonic oscillator has that minimum energy. So classically, obviously, you can put a particle in the bottom of the potential well. You can just put a classical particle over here. And if it has 0 kinetic energy, then it has 0 potential energy. And the energy of the particle is 0, right? But in quantum mechanics, you cannot do that, because you cannot just say the particle is here, because the wave function has a spread. If you just try to squeeze the particle to a single point, then the momentum uncertainty would increase. Okay, so this thing has a certain size, and because of that certain size, you are going to get some wave function spread, and that corresponds to some 0 point energy. Now this is important, yes.
Omega C.
In the end, sorry,
Omega C.
omega c.
Okay.
But in the end, we couldn't decrease below zero because of a boundary condition. But still, each a minus operator decreases the energy by minus h omega c. So, what is the reason that the last one is by an amount of minus 1/2?
Well, okay. The last point here, when you operate on this with A minus, you don't really get a state with zero energy. You don't get a state, okay? So what happens here is when you have this U0 of x and you operate on it with an A minus, okay, you actually get 0, okay, which means that this object here is your, if you like, U minus 1. And that might have energy minus h bar omega c over 2. So it might still have correspond to that, but there's no such state. Okay, so the state itself is equal to 0. So it's not really lowering the energy by half omega c over here because the energy is not reduced to 0. The wave function is reduced to 0. Okay. Other questions? All right. So we have all of these states. Okay, as I was telling you that there's this 0-point energy which becomes important for any harmonic oscillator type of system. For example, even for the electromagnetic energy, normally, classically, we would say, well, if there's no electromagnetic field in space, then there's no electromagnetic energy. But electromagnetic wave is also a harmonic oscillator, okay? And it does also have a 0-point energy. So even if you have 0 photons at a certain frequency, that corresponds to some energy. So that means the whole space has some energy for any frequency that you can imagine about. So it's an infinite amount of energy. So you could say, well, it doesn't really make sense because if it's infinite, then, okay, I can just ignore this some constant energy. But you see what happens is if you take, for example, two materials, two conductors, and the space between them has standing waves for all kinds of electromagnetic waves. As you move these conductors, the space between them changes, so the structure of the standing waves change, which means the energy associated with them, the 0-point energy associated with them changes. So there's a force between these conductors. It's very small, comparable to gravitational force, but it's called the Casimir force. Okay, so if you are more interested in that, Casimir effect. So this is some measurable amount of force, which is just a change in the infinite amount of force in space due to changing positions of conductors. Yes?
Professor, in free space, what is oscillating? I mean, there is in potential, there is oscillating term, right? So, what is oscillating is the first question. And then, yes, this is just one question. What is the oscillating?
Okay, what is oscillating? The oscillating stuff here in the harmonic oscillator with a mass is the wave function. Okay, what the wave function corresponds to physically is something abstract. Okay, so sometimes it's called matter waves and such things, but it is not something that is actually measurable. The wave function is not directly measurable. In the case of electromagnetic waves, those are the electric and magnetic waves, okay, magnetic fields, which are, in some sense, measurable. Okay. Yes.
You said that we cannot have the 0 point as a valid state because it doesn't satisfy the uncertainty relation. So does it mean the first state we got is similar to Gaussian wave packet?
Yes. Let's in fact look at that. Okay. So so we have not specified any wave function or anything of that sort up to this point, and we have just used this nice algorithmic procedure using these operators a plus and a minus and such things. So maybe it's time to look at what these wave functions look like. Okay, so I know that for the ground state, I have a minus times u0 of x is equal to 0, right? So I'm going to get an equation which looks like x over x0 plus I p over p0, u0 of x is equal to 0, or x over x0 plus I, in place of p I'm going to put h bar over I d dx, and a 1 over p0 someplace. Okay, u0, let me parent this again, u0 is equal to 0. Okay, so the i's cancel, and I have d dx u0 is equal to, please check my algebra, there's going to be a minus x0 h bar over p0, no, other way around, yes, no, that's correct, x0 times x times du0 dx. Right? Is this correct? Let's check the units. X, the x's cancel. X. Is this correct? I can. X0 is down here, right? X0, P0. No. Please check my algebra so that we get the correct result here. This is 1 over P0 is already there. H bar is up there. Okay. No, why would I? Okay, let me just do this again. Sorry. D u0 dx is equal to minus, okay, x over x0, right? And p0 over h bar, p0 over h bar u0. Okay, that seems to be okay. Okay, so x's cancel, x0, 1 over x. Okay, at least the units are correct. Okay, so I have something like this. Now, so we have to now solve this differential equation. The solution to this gives us u0. What type of a function will give you a solution? Hmm? Well, there's an x here. Careful. So what type of function will give you an x times itself?
X squared over 2.
Okay, well, okay, e to the minus x squared is, okay, but let's just try something like, say, u0 is equal to e to the minus alpha x squared, right? So the u0 dx is going to be minus 2 alpha x e to the minus alpha x squared. Okay, so we said this was u0. So in order to satisfy this minus 2 alpha, okay, minus 2 alpha must be equal to, well, just 2 alpha is going to be equal to p0 over x0 h bar. Okay, so that means this gives you a solution which has the form some constant, which we have to determine by normalization, e to the minus alpha, okay, which is minus p0 over x0 to h bar x squared. Okay, so it's indeed a Gaussian. Okay, so it's indeed a Gaussian. The p0 and such things, unfortunately I erased, but you can put these things p0 over x0. I think it's square root of km, right? Or km. In any case, just put these things in. Yes.
Is there any physical meaning of expectation value of a minus or a plus?
No. We'll see that they are not physical, they are not operators which correspond to any physical objects, physical properties.
I thought when they are Hermitian, they correspond to something.
They are not Hermitian.
Okay.
They
Okay.
are anti-Hermitian, right?
Well, we'll see.